Yeah, dear students, I'm G.K. Raghavan from All Fours Educational Institutions. Welcome to the Session 5 Chemistry All Fours e-learning program. Today, let us take up some numerical part of atomic structure, that is numericals based on wavelength, frequency and wave number. Okay, so in the last session 4 we had discussed about the complete information about properties of light, that is wavelength, frequency and wave number, velocity of light and amplitude. The theory process is completed in the last class. Now today we'll discuss about the numerical part and their relations between the properties. Okay, let us take the first problem, that is first one. Calculate the frequency of radiation having wavelength 4000 angstroms. Calculate frequency of, I'll write here, calculate frequency of light, that is electromagnetic light. Electromagnetic light. Calculate the frequency of electromagnetic light having wavelength. Having wavelength lambda, that is 4000 angstroms. 4000 angstroms. Now the lambda value is given, that is equals to 4000 angstroms. Okay, then we have to calculate frequency of the light. Nu we have to find out. Now the related formula for this is nu is equals to C by lambda. Nu is equals to C by lambda. So this we have to consider. Nu is equals to C by lambda, where C is the velocity of light. C is the velocity of light and its value is constant, that is 3 into 10 to the power 8 meters per second, or you can consider 3 into 10 to the power 10 centimeters per second. Okay, right. Nu is equals to C, velocity of light, let us consider in meter per second. 3 into 10 to the power 8 meter per second by lambda value, that is 4000. That is 4000 into, as we know that 1 angstrom unit is equals to 10 to the power minus 8 centimeters or 10 to the power minus 10 meters. So consider in, that is 10 to the power minus 10 meters. 10 to the power minus 10 meters. That is, yes, on solving this one, that is equals to, that is 3 by 4. This is nothing but 10 to the power minus 7. Okay, when it goes up it becomes 10 to the power positive. So that is into 10 to the power, okay, 10 to the power it is 7. So it becomes 10 to the power 15 meter, meter cancel, it is second inverse. So therefore 3 by 4, that is nothing but 0.75 into 10 to the power 15 per second, that is, or 7.5 into 10 to the power 14 second inverse. So this is the first problem. Okay, So that is, we are calculating the frequency of the electromagnetic light having wavelength 4000 angstroms. So 4000 angstrom, that is 1 angstrom unit is equals to 10 to the power minus 8 centimeters or 10 to the power minus 10 meters. Okay, right. Next, let us take up, that is frequency of the light. Now, let us take the second problem. Okay, so first problem is clear. So we are calculating, that is when wavelength is given, we can calculate frequency of the light. And see, we can also define velocity of light. C is equals to, velocity of light is equal to the product of frequency of the light and wavelength. Okay, so sometimes you can also expect, so velocity is equal to the product of, you will find 4 different options like frequency and wavelength, and sometimes frequency and wave number, like that. Okay, right. Next, let us go to the second problem. So let us leave these constant values. Now the second problem is, so the second problem is calculate wave number of the radiation, having wavelength 4000 angstroms. Again, let us take the 4000 angstroms. Calculate wave number of radiation. Calculate wave number of radiation having wavelength 4000 angstroms. Now in this, lambda is given, wavelength is 4000 angstroms. Okay, and let us consider that 1 angstrom unit is equals to 10 to the power minus 8 centimeters, or that is equals to 10 to the power minus 10 meters. Okay, then we are calculating wave number. Okay, calculating wave number. So nu bar is equals to 1 by lambda, that is wave number is reciprocal of the wavelength. Okay, so now nu bar is equals to 1 by 4000, that is 4 into 10 cube into 10 to the power minus 10, it is meters, that is equals to 1 by 4 means 0.25. This is nothing but 10 to the power minus 7 it becomes. So into 10 to the power minus, so when it goes up it becomes plus 7. 10 to the power 7, that is meter inverse. So or we can say it is 2.5, that is equals to 2.5 into 10 to the power 6 meter inverse. This is wave number of the electromagnetic light. Okay, in this problem, calculate wave number. We have to calculate the wave number of the electromagnetic radiation having wavelength. How much it is given? It is 4000 angstroms. Okay, so lambda is 4000 angstroms, and we know the centimeters and meters. Okay, now nu bar is equals to 1 by lambda, that is nu bar is equals to 1 by lambda value is 4000 into 10 to the power minus 10 meters. Okay, so that is 1 by 4 is nothing but 0.25. So this is 10 to the power minus 7. When it becomes positive, so 0.25 into 10 to the power 7 meter inverse, or that is equals to 2.5 into 10 to the power 6 meter inverse. Okay, this is the second problem we have done. Okay, this is second problem, the relation between wave number and wavelength. Okay, next let us take up the third problem. Third problem is Yeah. See, for example, Vividha Bharati All India Radio Station. Vividha Bharati All India Radio Station broadcasts, I'll write, Vividha Bharati Radio Station broadcasts on a frequency 1368 kilohertz. 1368 kilohertz. Calculate wavelength of the radiation emitted by the transmitter okay. So we have to calculate, that is frequency is available, and we have to calculate, that is wavelength. Okay, so as we know that nu is equals to c by lambda. Okay, now you are calculating wavelength, so now lambda is equals to c by nu. Okay, so you are calculating the wavelength of the light, that is radiation emitted. Okay, now c is equals to velocity of light, that is 3 into 10 to the power 8 meter per second by the frequency of the light, frequency of the radiation, that is 1368 kilo. So 1368 kilohertz, that is 10 cube. Okay, so on solving this, yes, so it is meter cancel, so now it is frequency per second. Now it is 0.0029 meters. So R, that is into, it is into 10 to the power, so when it goes up it becomes 10 to the power 11 meters. C is the velocity of light and frequency is this much kilohertz. Okay, so R, that is equals to, when you take the decimal, so that is 1 2 3 4 5, so it is becomes 10 to the power 5. So now it is 1 2 3 4 5, so it is 219 meters. So that is the answer, final answer. So that is wavelength is equals to 219 meters lambda. Okay, so this is calculating the wavelength of the radiation. Yes, so now coming to the next problem. Okay, yes, in this problem, visible spectrum having wavelength range 400 to 750 nanometers. So the wavelength range is given in terms of nanometers, and calculate its frequency range. So we need to calculate frequency of that visible spectrum. Okay, so now nu is equals to, the same formula we have to use again, nu is equals to c by lambda. Okay, so this is nu is equals to c by lambda. Now let us take the first one. Nu is equals to c, 3 into 10 to the power 8 meter per second by wavelength, that is 400 nanometers. As we know that 1 nanometer is equals to 10 to the power minus 9 meters. So therefore it is 10 to the power minus 9 meters. So then that is equals to, so 3 into 10 to the power 8 divided by 4 into 10 to the power minus 7. This is equals to 3 by 4 into, when it goes up it becomes positive, that is 10 to the power 15, that is per second, that is equals to 0.75 into 10 to the power 15 per second, or 7.5 into 10 to the power 14 second inverse. This is frequency of the light of wavelength 400 nanometers. Now the second part, so that is nu is equals to, we have to calculate frequency for 750 nanometers. So now again nu is equals to 3 into 10 to the power 8 meters per second divided by, that is 750 into 10 to the power minus 9 meters. Okay, then nu is equals to 3 into 10 to the power 8 divided by 750. Okay, when it goes up it becomes 9. That is equals to 3 into 10 to the power 17 by 750. Okay, and from this, so the calculation, that is equals to 0.004 into 10 to the power 17, that is per second, or that is equals to 4 into 10 to the power, so that is 3 zeros, it is 14 second inverse, that is frequency of this light. Okay, then what is the frequency range? He is asking frequency range of the visible light. So the frequency range we can say that is 7.5 into 10 to the power 14 per second to 4 into 10 to the power 14 per second. That is the frequency range of the visible spectrum, that is visible light. So this is interesting problem having, that is calculating frequency, and wavelength is given as 400 to 700 nanometers. So that is visible spectrum, that is VIBGR. So starting from violet and ending with the wavelength 750 nanometers, that is for red colored wavelength. So violet to red, that is the wavelength range of the visible spectrum. So this point is also can be noted as important point for the objective examinations. Okay, so this problem is over. So we can calculate different frequency, wavelength and wave number. Yes, now so that is the nature of light is almost completed, because in the last session only we have taken nature of the light as, that is particle theory of light and wave theory of light and electromagnetic theory of light we have done, and properties of the electromagnetic light, that is such as wavelength, frequency, wave number amplitude, and we have done the numericals based on these concepts also just now completed. Now let us take up electromagnetic spectrum. The new topic is electromagnetic spectrum. Electromagnetic spectrum. What is meant by spectra? Spectra means it is a group of light, means group of wavelengths, or we can say a group of frequencies. Okay, so in the spectrum, each light having its own characteristic wavelength and frequency. So therefore we can say the group of wavelength is considered as spectrum. Okay, so we have electromagnetic spectrum. Okay, that means the radiation now we consider as electromagnetic light. So therefore it is nothing but electromagnetic spectrum. We have various electromagnetic radiations. The systematic arrangement of the electromagnetic radiations in the increasing order of their wavelength or decreasing order of their frequency is known as electromagnetic spectrum. Okay, so what are the electromagnetic radiations we have? One like cosmic rays, gamma rays, cosmic rays, gamma rays, X-rays, UV rays, ultraviolet radiations, X-rays, UV rays, ultraviolet radiation, then visible light, and then infrared radiations, and then microwaves, and the last is radio waves. So the various electromagnetic radiations. So all these electromagnetic radiations are arranged. They are arranged in the increasing order of their wavelength. So now in this, the wavelength of these radiations is in the increasing order. That is, wavelength increases. Wavelength is increasing order. That means radio waves possess maximum wavelength. Lambda is maximum for that. Maximum lambda, and it is they possess, that is cosmic rays, they possess minimum lambda. So that is wavelength. Now when you say frequency of these electromagnetic radiations, so frequency that is, so it is increase, as we know that nu is equals to c by lambda. That means when wavelength is maximum, frequency will be minimum. So therefore radio waves possess minimum frequency, and whereas cosmic rays possess maximum frequency. They possess maximum frequency. So that is, once again, the definition of electromagnetic spectrum is the systematic arrangement of various electromagnetic radiations in the increasing order of wavelength or decreasing order of frequency is known as electromagnetic spectrum. So wavelength is increasing and frequency is decreasing. Okay, that we should remember. So now you can expect the questions like, see for example, the infrared, that is, which among the following possess greater wavelength than visible light? Greater wavelength than visible light. I repeat the question again. Which among the following has greater wavelength than visible light? Okay, that is the question. Now let us see the options like gamma rays, first option. Second option is X-rays, and third option is infrared rays, and fourth option is UV rays. Which among the following possess greater wavelength than visible light. Greater wavelength than visible light. Visible light is this one. So greater wavelength means after this. So that is, so gamma rays, X-rays and UV, they possess shorter wavelength than visible light. Infrared radiations possess higher wavelength, that is greater wavelength than visible light. So answer will be IR, infrared radiations. So like that, the important theory questions you can expect from this electromagnetic spectrum. Okay, done. Fine. Next, let us see what are the sources of these electromagnetic radiations. See, in academy books, so it starts from gamma radiations. That is, in the updated books, so they have cosmic rays. So in our academic book, they starts from gamma rays onwards. Okay, let us see what is the source of these gamma rays. Let us see the sources of various electromagnetic radiations. Okay, so gamma radiations, gamma rays. Gamma rays are produced from the nuclei of unstable radioactive isotopes. Gamma rays are produced from the nuclei of unstable radioactive isotopes. That is one, gamma rays. And let us see X-rays. X-rays are produced when a stream of cathode rays hitting on the surface of a metal. When a beam of cathode rays hitting on the surface of metal, it produces X-rays. That is the source of the X-rays. Now coming to the UV. UV radiations are produced from, one important source is sunlight. Okay, so the UV radiations are produced from the sun. And second one is mercury vapor lamp. Mercury vapor lamp can also produce ultraviolet radiation. And xenon arc lamp also produce UV radiation. Okay, next, visible light, the source of the visible light. So visible light is produced from sun, stars and incandescent solids. What are the sources of visible light? Sun, stars and incandescent solids, means the solid which glow on heating, that is called incandescent solids. Okay, so example for this incandescent solid, that is electrical bulb filament. So on switching on the light, what happens? So the electric bulb, the filament, the solid filament heated up and glows. So that can produce visible light. Infrared radiation is produced from Nernst Glover and Glover source. Okay, and microwaves are produced from klystron tubes. They are produced in klystron tubes. So these microwaves are used in telephone and telegraph circuits. Okay, so that is completed. Now radio waves. These radio waves are produced by alternating current of high frequency. Okay, so radio waves are produced by alternating current of high frequencies, right? So these are the various electromagnetic radiations. Okay, so then after this, let us take up the classification of spectra. Classification of spectra. So now, what is a spectra? So we had a introduction about the spectra, means it is a group of wavelength, that is done. Now we are going for classification of spectra. The spectra is basically classified into two types. One is continuous spectra and second one is discontinuous spectra. What is meant by a continuous spectra? Spectra is basically classified into two types. Spectra. One, continuous. Continuous spectra. The spectra in which the spectral lines are arranged closely without any gap between the spectral lines, that is called continuous spectra. Okay, the spectra in which the spectral lines are arranged closely. The spectra in which the spectral lines are arranged closely without any gap, that is called. See, for example, the spectral lines are arranged without gap. The spectral lines are arranged without gap. So now all the spectral lines are arranged without any gap. So that is called continuous spectra. Okay, example for continuous spectra, that is light spectrum. Best example, light spectrum. So in that light spectrum we have 7 colors, WIBGR. So all these 7 colors are arranged closely without any gap. So they are belongs to continuous spectra. Okay. Second one is discontinuous spectra. Discontinuous. Discontinuous spectra. Discontinuous spectra. The discontinuous spectra is the spectra in which the spectral lines are well defined with gaps. The spectral lines are well defined with gaps is called discontinuous spectra. That means the spectra in which the spectral lines are well defined with gap is called discontinuous spectra. Okay, so right, this is a simple definition to understand the continuous spectra and discontinuous spectra. The example for discontinuous spectra is we have emission spectra, absorption spectra. Okay, many are there. Okay, now the discontinuous spectra is further classified. Discontinuous spectra is further classified into 2 types, that is emission spectra and absorption spectra. One is emission spectra and number 2 is absorption spectra. Absorption spectra. Emission spectra and absorption spectra. Now let us take the first one is emission spectra. Emission spectra.